Back in 2021, a team at Microsoft dropped a paper that would completely change the game for customizing large AI models. It's called LoRA, Low Rank Adaptation of Large Language Models. And its central idea is so simple, so elegant, that it's become an absolute pillar of modern AI. So let's dive in and see how this one clever idea works and why it really did change everything. So here's our roadmap for today. We're going to start by setting the scene with the huge problem everyone was facing. Then we'll get to the aha moment, the core insight behind LoRA. We'll pop the hood and see how the method actually works, check out the incredible results, and then talk about the massive legacy it's left behind. And we'll wrap up by looking at some cool ideas it's sparking for the future. All right, so to really get why LoRA was such a big deal, you have to picture the AI world back in 2021. This was the time of giants. We had models like GPT-3 with its mind-boggling 175 billion parameters doing some truly amazing things. But there was a massive catch, a really, really big one. See, if you wanted to teach a model like GPT-3 a new trick, a process we call fine-tuning, you had to update all of its weights. And what did you get at the end? A brand new, specialized model that took up a whopping 350 gigabytes of storage. And that was just for one single task. I mean, just let that sink in. Imagine you're a company. You need one AI to summarize legal documents, another to translate German, and a third to help write marketing emails. Well, congratulations, you now need 3 separate 350 gigabyte copies of that model. It wasn't just inconvenient, it was a total deployment nightmare. It was way too expensive, both in hard drive space and in the computing power needed to run it all. Back then, you were basically stuck between a rock and a hard place. You could go with full fine-tuning, which gave you top-notch quality, but, came with those crushing storage and compute costs. The other option was something called adapter tuning. This was smarter. It added tiny new layers to the model. Much more efficient for sure, but it had a fatal flaw. It added extra steps to the process, which meant your model got slower. That trade-off between efficiency and speed was a huge bottleneck, and everyone was looking for a way out. And that is where the LoRA paper comes in with its brilliant insight. The authors were inspired by this idea that these huge, over-parameterized models are actually operating on a much simpler, lower intrinsic dimension. So they thought, hey, what if we apply that idea not to the whole model, but just to the changes we make during fine-tuning? And this quote right here, this is the magic. Their big bet was this. The change you need to make to the model's weights to teach it a new skill doesn't have to be a massive, complicated overhaul. They hypothesized that this change, this delta, could actually be represented by something much, much simpler, a low-rank update. So what the heck is low intrinsic rank? Think of it like this. Your pre-trained model is this enormous, super complex master file in Photoshop. Now, if you want to make a new version for a client, you don't have to start from scratch and remake the entire thing. No, you just add a small, simple adjustment layer on top. Maybe you just tweak a color or change a font. That little layer is the update. It's simple, it has a low rank, and that was the epiphany. Fine-tuning doesn't need to be a new model. It can just be a tiny adjustment layer. Okay, that's the big idea. But how did they actually build it? This is where things get really elegant. Instead of trying to learn that giant, complex update matrix directly, they found a way to break it down into smaller, manageable pieces. Let's just walk through this, because it's awesome. First, you take the original model's weights, we'll call them W0, and you lock them down, freeze them. You never, ever change them. Second, you add 2 brand new, super tiny, low-rank matrices, called B and A, right next to the original weights. Third, and this is the key, you only train those 2 little matrices. That's it. Finally, when the model is running, its output is just the result from the original weights, plus the result from your tiny new BA matrices. So simple, but so powerful. And this table just drives the point home. Look at this. A single weight matrix in something like GPT-3 might have over 150 million parameters. That's totally frozen. The LoRA update, on the other hand, these 2 little B and A matrices, with a rank of just 4, they have less than 100,000 trainable parameters combined. You're training a tiny, tiny fraction of the original size. It's just a completely different scale. Okay, this all sounds amazing on paper, but the proof is in the pudding. Did it actually work? Well, the researchers tested LoRA on a ton of different models and tasks, and the results were, frankly, spectacular. This is the number that got everyone's attention. compared to doing a full fine-tune of GPT-3. LoRA cut down the number of trainable parameters by a factor of 10,000. That 350 gigabyte monster file we talked about, it's now a lean 35 megabytes. That's not an improvement, that's a revolution. And this chart just says it all, doesn't it? On one side, you've got the skyscraper of 175 billion parameters for full fine-tuning. On the other side, the LoRA update is so tiny you can barely even see it on the same chart. The difference is absolutely staggering. But here's the absolute kicker. This massive reduction in trainable parameters came with basically no hit to performance. Actually, check this out. Sometimes it was even better. On the Wikischool task, LoRA is right there, performing on par with the fully fine-tuned model. And on the Samsung summarization task, LoRA actually beats the huge baseline. All of that while training a minuscule fraction of the parameters. It was definitive proof that you could get all the quality without any of the crushing cost. So why does all this matter so much? Because LoRA wasn't just some clever math trick. It completely changed how we think about customizing AI. It basically democratized the whole process, making the power of these giant models available to pretty much anyone. The benefits here are just total game changers. Storage costs basically vanish. The hardware you need for training gets way cheaper. The paper showed up to a 3 times reduction in GPU memory usage. And critically, this is huge. There's no extra lag or latency when you use the model because you can merge the LoRA weights right back into the main model before you deploy it. Plus, you can have one base model and just swap these tiny megabyte-sized LoRA files in and out to switch tasks on the fly. It's just incredibly efficient. This all brings us to today and to the future. The core idea behind LoRA, these simple low-rank updates, is so fundamental that it's opening doors to all sorts of fascinating new ideas. The original paper played around with different fixed ranks, like a rank of 4 or a rank of 8. But what if the model could figure out the perfect rank for any given task all by itself? You could imagine a system, let's call it adaptive rank LoRA, or AdaLoRA. In this kind of system, the model itself would decide how much power it needs for a new task. For something simple like basic classification, maybe it only needs a rank of 1 or 2. But for a really tough, complex reasoning problem, it could scale itself up to a rank of 32 or 64, allocating more horsepower exactly where it's needed most. You'd have this hyper-efficient system that automatically finds that perfect sweet spot between performance and cost for any problem you throw at it. This is for entertainment purposes only.